Hello everyone, welcome back. So today we're going to be learning about Poisson's ratio. Poisson. It means fish, but it was actually the person's name, so that's why we have the name today. Now, what is this? Why do we care? Well, we'll get into that soon. But first off, you remember this, how we had that necking earlier and then it had failure? Well, the cross-sectional area is decreasing. Now in this case, it's decreasing locally. That's dangerous, but before that point, it was decreasing, over the entire surface. It went from maybe this down to this, and then it began necking. So we realized that happened. We have some sort of strain, and then it gets maybe thinner or fatter in the center. But how can we quantify this change in cross-section? And is it even important? Do we care? I mean, yeah, we care here, but other than that, do we care? Well, the way we figure this out is from Poisson's ratio. So you'll have some initial shape and we apply a load. If it's tensile, it's going to get thinner. If it's compressive, it's going to get fatter. And this is because we have to change our cross-section to maintain our volume. We're not necessarily to maintain volume, but just to maintain continuity. The bonds will break way quicker if they don't do this. Now, if you actually think about atoms as, being connected by springs, let's say something like this, okay? And they're all connected to springs because they're all connected to each other. Well, if these are all springs and I start stretching it in this way, what's going to happen? Well, these are going to get closer together. They have to. It's the way they're minimizing the force on them. If they try to stay separate, there'll be a lot more force, and so they come together. And so that's the same thing that happens here. As we stretch it, these begin to push against each other or pull against each other, and it brings these atoms on the top and on the bottom together in order to minimize the force. So that's the microscopic reason for why we see Poisson's ratio. Now this follows a nice and easy equation, which is simply we have our longitudinal strain, longitudinal, and then we have our lateral strain, which is going to be the cross right here, one of those. So Poisson's ratio will be the negative of that. If you're wondering why is it negative, it's because if you stretch one, it will have a positive strain and the other one will have a negative strain. It will always be opposite. It'll never be the same thing. So Poisson's ratio will always come out to be a positive number. Now, if we compress it, the exact opposite will happen. And this is constant. At least it's constant until we start getting into those crazy inelastic plate regions or when we get to necking. Now, this constant cannot be greater than 0.5 in order to maintain the total volume of material. If it's greater than that, it's not going to work. One other important factor can be learned from this. Now, we had a modulus of elasticity, and I mentioned earlier, we had the shear modulus to G, and I said that these two are connected. And you're like, well, how are they connected? And I said, we'll figure it out later. Don't worry about it for now. Well, today we figured that out, and here is the connection. They're connected through Poisson's ratio. Now, why is that? Well, look at it this way. Remember how we talked about shear strain? It's kind of how we change a cross-section. We're changing a cross-section when we do this. Well, we're also changing the area of that cross-section when we do that. And because of that, if we change the cross-sectional area, it's going to cause it to expand or contract. And therefore, it will be connected through Poisson's ratio. So one will lead to the other. Each of them are going to lead to the other. Some sort of shear strain or shear stress eventually. So I think that's everything for today. Yes, that is. So now let's actually get some practice with these problems to show you how to use these equations in a real, semi-real life situation. So thanks for listening. I'll see y'all soon. Bye-bye.